Welcome to qnawire.
Black bodies are present in outer space as stars, but a more common example is the filament inside of an incandescent light bulb. So that filament is basically inside of a vacuum, and so it radiates energy through electromagnetic radiation. And so the law that the filament follows is the Stefan-Boltzmann law. And I will write it with the non-ideal situation. But it says that the power a black body radiates depends on the emissivity, which is a property of the material, and is one for a perfect radiator. A constant called the Stefan-Boltzmann constant times the surface area of the radiator times the temperature in Kelvin to the fourth power. And that is an interesting law that the power radiated is very sensitive to temperature, or the temperature depends very sensitively on the power, however you want to think about that. Okay, so the idea is we have two light bulbs, and they have the same filament to start off with. It's not too easy to change a filament unless you're at the factory. But filament A operates at 2100 degrees centigrade. And here I want to point out that that temperature must be an absolute scale. So we will want to convert that to Kelvin by adding 273 Kelvin to that. And the second bulb is a little bit cooler, 2000 degrees centigrade, but we want to convert to Kelvin to make it an absolute scale. And we want to compare the power output, power A to power B. And everything is the same about these two bulbs, including the material they are made out of. So all the constants will disappear except for the temperature. So that ratio will depend on the ratio of the temperatures raised to the fourth power. So they don't differ that much by temperature, only by a few percent. But by raising that to the fourth power, you see that bulb A radiates about 18.8% more power. Okay, and let's say that the company did not want the second bulb to radiate less power. So the idea is that the filament, okay, I've kind of show it bent in a loop. They usually are squeezed into the bulb in such a way that the surface area doesn't look like it occupies that much space. But they're basically cylinders. And what we want to do is change the radius of a cylinder on B so that the power B equals power A. So now we are going to have to compare the ratios of their areas as well. So the surface area of a cylinder is a pretty easy thing to work with. So it depends on the circumference, 2 pi r, times the length. So we want power A and to equal power B. And that means that the temperature of A raised to the fourth power times its surface area has to equal the same thing for the second bulb. Okay, and the only thing that is going to be different between the two is the radius. So radius of A, temperature of A, is equal to radius of B times temperature B raised to the fourth power. And we can then solve that for the radius of the B is simply that same ratio of the two temperatures raised to the fourth power times the radius of A. So that same 18.8% number that we looked at for the radiative power, we're going to have to boost up the radius. Okay. So that is a good thing to know.